Talk about faceting is one of my favorite technical conference talks. It's done by my friend and colleague Ants Aasma. It's very technical, but it's not very deep, so you can crack it. And that's why it's really interesting for everyone.
Open any large catalog. Every filter you click, the panel on the right updates with the exact count of matches in less than a second. How is that possible? Faceting is counting on steroids. Every filter you add runs a grouped count over every matching row for every attribute on screen. Too many combinations to pre-compute. Some filters are unselective and have to tally a huge fraction of the table. Users expect it to feel instant. Consultant Ants Aasma tried the obvious thing on 100 million rows. 4 grouped counts, union together, 32 seconds, 1 scan via a lateral join, 23.4 seconds, 24 workers, 16.8 seconds, and that is only 4 facets. This is not scaling. Let us do the math. For each row, for each facet, you find a counter and add 1. 100 million rows times 10 facets, a billion lookups. One memory access is about 100 nanoseconds. A billion of them, 100 CPU seconds. Here's the catch. In the time it takes to fetch one number from memory, light travels 30 meters. A billion fetches is to the moon and back 100 times. Random access is slow. What are CPUs fast at? Bit arithmetic and vector execution. 3 instructions do almost all the work. A 512-bit vector AND reads 2 operands and produces a result. A pop count counts the ones in 864-bit words. A vector add adds 2 vectors. A modern core issues about 1.5 billion of these per second. Multiply by 512 bits and you get roughly 1 trillion bit intersections per second per core, a third of a light millimeter per bit. Now we change the problem. Instead of a counter per attribute value, we build 1 bitmap per attribute value. The bit at position ID is 1 if that document has that value, 0 otherwise. Then a facet count is the pop count of the AND of 2 bitmaps. This is not a new idea. It is the same idea as the GIN index in Postgres or Lucine's postings list. Sounds great. So why is this not how every database does it? 10 facets times 1,000 values times 100 million bits is 1 trillion bits. 125 gigabytes. A single core can only pull about 10 gigabytes a second. The numbers do not work until you remember one thing. 99.9% of those bits are 0. Some values are popular, most are rare. Compress adaptively. That is what roaring bitmaps do. Daniel Lemire and friends published the design in 2017, split a 32-bit ID into a high half and a low half, 16 bits each. The high half is a sorted list of which blocks have data. Each block points at one of 3 container kinds, a sorted array of low halves, up to 4,000 entries, an 8 kilobyte bitmap, or run length pairs. Pair the containers between 2 bitmaps and run the right operation, picked at runtime, per block. A Postgres extension wraps the C library, a roaring bitmap data type, a build aggregate, bitwise operators, an AND count in one pass. Building all the facets for the 100 million rows takes 34 seconds. The whole facet table is 214 megabytes, about 2 bytes per document. The first facet query runs in 1057 milliseconds. The explain plan shows every toasted bitmap being detoasted at the wrong moment. The fix is a shift by 0 no-op that forces the planner to defer detoasting. 80.1 milliseconds, 400 times faster than naive, 25 times under the 2-second budget. One last problem. Inserts rewrite megabytes of bitmap data, so chunk the ID space into 1 million row ranges, roughly 10% faster and a fraction of the write cost. Then buffer inserts and deletes in a small delta table and merge them in periodically. All of that ships as a ready-made extension. Declare your facets, ask for counts, run maintenance on a cron, sponsored by Zenit. The same trick powers more than faceting. Number your graph nodes with integers. Store each node's outgoing edges as a roaring bitmap. 2 frontiers, one from the source, one from the destination, expanding by 1 hop each step. They meet in the middle. Bidirectional breadth first shortest path in plain SQL. So the lesson is this: turn counting into bit parallel set algebra, compress adaptively, and count at the speed of light. Thanks to Ants Aasma at Postgres Conference Europe 2023 and Nordic DevOps Days 2025. Links in the description.